Assalamu alaikum. Welcome everyone to this physics course for O-Levels and IGCSE physics. Now, before I start, just a little bit about myself. So my name is Muhammad Usman Shaukat, and I did my A-Levels and O-Levels from Hson College, and I'm from the batch of 2015. After that, I went to Purdue University in USA and did my Bachelor's of Science in Electrical Engineering. And throughout my college career, undergraduate college career, I did a lot of teaching. I have taught for about 3 years, and I was officially employed by the undergraduate department of electrical engineering at Purdue to serve as a peer tutor. So I love teaching, especially physics. I'm always looking for answers, and the biggest question for me is, who am I? And I'm still figuring that out. So that was just a little bit about me. So moving on, the format for these lectures will be basically divided into 3 steps. I will introduce a concept, and then I will quiz you on a concept, and then we will do some past paper practice. Now, this is very, very important. No matter how much you learn something or how much knowledge you gain, one thing that I've experienced is that unless you practice what you've learned, it's if you don't practice, it's basically useless. So knowledge without practice is useless. So paper practice, I can't emphasize enough. It is very, very important. And so we'll focus on that a lot. All right, so moving on. So this is the syllabus for O-Levels. If you're taking IGCSE, that's fine. O-Levels and IGCSE are pretty much the same. So basically, the physics of O-Levels and IGCSE is divided into 6 sections. Each of them have these various topics, and we will cover all of them one by one. So the topic for today will be physical quantities, units, and measurement. But before we start, diving into the syllabus and into the sections and the topics, there's something that I want to ask you, and that is, what is physics? Have you ever thought about it? Just look around you for a second. There's probably a bulb turned on or some source of light. Now that source of light is the same for every object that you see, right? Every object in your room receives the same light. But even though they receive the same light, you see different colors. Now why is that? Right now, at this very moment, you're watching this lecture and you're breathing, but you weren't concentrating on your breath. Now, if you do concentrate, you'll see that when you inhale, your chest expands, and when you exhale, your chest contracts. And why is that? Right? So physics is what answers these questions. So basically, physics is the study of all physical phenomena experienced by our human senses, the 5 human senses, either directly or indirectly. It is based on experiment and observation and is made quantitative by mathematics. So I think this is very, very important. Before studying something, we should at least know what it is. Because if we do, I think that will make things a lot interesting when we study them. All right. So whenever I start a topic, before starting, I will talk about or I will present the learning outcomes. By the end of the chapter, by the time we finish the chapter, we will come back to these learning outcomes and see what we've covered, and what we've not covered. And we want to make sure that we've covered everything because, these learning outcomes are stated in the syllabus for O-Levels. And this is what you will be tested on. So it's quite important. All right. So physical quantities. Everything around you, everything that you see around you is a physical quantity. All right. And so it's a property of a material or a system that can be quantified by, measurement. For example, mass, length, or time. Right. And there are these 3 fundamental units that exist: mass, length, and time. And the standard units for them are basically the SI units are the kg, the meters, the meter, and the second. And all other units, they can be derived from these three fundamental units. Now, this is a table that you should probably memorize. In the exam, you'll be given a base quantity, and you'll be asked for what it stands for and what the SI unit, for this is, for like one of these quantities is. So this is memorization. Okay. Now, before we move on, we need to talk about the International System of Units. So basically, why was this International System of Units developed? Well, there are two reasons. First, we need a standard to measure the physical quantities, right? We can't just start measuring something without a reference point. And the second thing is to keep uniformity around the world. Now, if you allow me to explain, the thing is, you're sitting in your home. If I ask you what your location is, right, you won't be able to tell me your location unless you know some point of origin. Like, unless you know some origin, you can't really tell me your location. What do I mean by that? For example, I draw this point right here. I ask you, tell me what the location of that point is. Well, you'll be confused. You don't know what that position is going to be, because you don't know where to start from. So what you do is, now if I draw a y-axis and an x-axis, and I say that this is the origin, and I'll somehow divide this into some steps. Okay, let's say one division's one step. Okay, now that you know the origin, you can say, okay, I know what my location is. It's 3 units to the right and then 2 units to the north. Okay, so basically we needed a standard to measure these physical quantities. Okay, now mass, length, time, they're all these physical quantities. But if I say, for example, 10 kgs, right, what does 10 kg mean? So what happened was that physicists defined a standard. What they did was, for example, this is just an example. Let's say they found uranium, or they found some kind of a rock somewhere. What they did was they extracted a piece of this rock, right? And they preserved it in a laboratory, and they placed that piece inside. And they said, you know what? The mass of this object is 1 kg. That will serve as our reference point. Now, everything that I measure from this point onwards, if I say, what's 10 kg? Basically, now I have a standard. I'm like, okay, I know what 10 kg feels like, or I have an idea of what 10 kg is, because I know what 1 kg is, or what 1 kg what 1 kg means. I have a reference point, so I know what 10 kg is. It's just 10 times more heavy. I shouldn't be saying heavy. It has 10 times more mass than this small piece of rock. And the other thing is, this was very necessary because let's say someone in Pakistan was measuring length and they defined a different standard for 1 meter, okay? And someone in the USA was measuring length, but they defined a different standard for 1 meter. For example, in Pakistan, 1 centimeter was this much. And the US said, no, we're going to measure 1 centimeter as this much. So that was going to create problems. And so what happened was that this international system of units was developed so that uniformity is maintained throughout the world when research is done and when experiments are done. All right. The last topic on this slide is significant figures. Now, before I talk about significant figures, the thing that I want to say is that there is a difference between accuracy and precision. Accuracy is basically how close to the truth are you. Okay, if I have something and I ask you to measure a physical quantity, how close am I to the truth and to the reality of the thing that I'm measuring? Okay, and precision, on the other hand, is that if I use an instrument to measure some specific quantity, if I use that instrument to measure the same quantity over and over again, how likely is it that it will give me the same value again and again? Now, what I mean by that is, let me give another example. Let's say that I have a circle and I ask you, what's the radius of this circle? Now, you can use a meter rule, place the meter rule at this point, and then measure the length and tell me, it's this much. However, the thing is, that's just an approximation. It's accurate, but it's not very accurate, right? What do I mean by why it's not very accurate? If I zoom in to the edge of this disk, if I give you a zoomed in view, you're going to see, using a microscope, we're going to see that, the edge of this disk is actually quite rough, okay? That this smooth edge was when we zoomed in, it looked like this. And so when we use a meter rule, we can't really measure those differences, like these small tiny differences. If we use a microscope that's even more powerful than this one, and it zooms even further, we can see more changes or more tiny differences. So we can't really measure everything to 100% accuracy. But we can get accurate if we use instruments that give us more significant figures. Now, what I mean by that is, for example, when you used a meter rule to measure the length between these 2 points, you got 2 centimeters, let's say. When you used a microscope and you did some, you found some way of accounting for these small changes, you measured 2.11234 centimeters, right? So these significant figures, in this case it's 1, 2, 3, 4, 5 significant figures. The greater the significant figures, the more accurate you are. All right, and what I mean by precision is, let's say I used the meter rule to measure this value and I got 2 centimeters, and if I use the meter rule again, let's say the next time I'll get 2.1 centimeters, and the very next time I'll get 2.05 centimeters. So this says, you know what? The meter rule is quite precise because it's giving me values that are close to each other. But if this happened, that I measured 2 centimeters in the first case, and the next time I measured, it was 2.5 centimeters, and then it was 2.1 centimeters. Now this is not very precise, okay, because the values are changing too much. So I hope you have an understanding of what accuracy and what precision is, and then what significant figures tell us about the accuracy. Okay, just one more thing to mention. We have this thing called subunits. We define these subunits to make our calculations easier. Let's say I have a point A and then a point B, right? And the distance that I measure between them, let's say that was like 200,000. Now, every single time I do these calculations, I don't want to keep, or let's say 2 million. I don't want to keep writing all these zeros, right? So what I do is that I introduce these factors. And I say, okay, I'm going to write down, instead of writing 2 million, I'm going to say that's equal to 2 mega. Because it has 6 zeros, I'm just going to say it's 2 mega. So if this is 2 million kilometers, I'm going to say it's just 2 mega kilometers. I shouldn't be saying kilometers. If it is 2 million meters, then I can just simply write that down as 2 megameters, right? So that makes things easy. All right. Now I'm going into a little bit detail in this topic. Usually I'm not going to go into this much detail. The only reason I'm going into detail is because I want you to get a good understanding of what physics is and why we use it. Moving on, I'm just quickly going to explain concepts and then, quiz you on them and then practice past papers. All right, so moving on. Units conversion. So you can either convert from high to low or low to high. Now the high to low method, what I like to think, the way I like to think about this problem is that think of the, let's just define what we want to do first. So let's say I know that 1 meter has 100 centimeters, right? That's something that I do know. So if I'm going from high to low, let's say I ask you, what's 6 meters equal to? Now there are 2 ways I can do this. One way is I'll say, okay, 1 meter has 100 centimeters. So how much centimeters are there in 6 meters, right? How many? So what I do is I do this cross multiplication. I'll say 6 times 100 equals to 6 times 100 is x times 1. All right, and we have to make sure that this x, which is the question mark, that's in centimeters. Okay, so x is 600 centimeters. The other way that I like to do this is think of the higher quantity like a container. Like, let's say it's like this container, and this container is 1 meters. All right, so if this is 1 meters, the smaller quantity, the lower unit that we want to go into, think of it as water that flows into this container. All right, how many centimeters can I pour into this 1 meter? And we know that we can pour in 100 centimeters for it to be 1 meter. So the other way we can solve this problem is that I can say, all right, 6 meters is going to be equal to, first you draw this parentheses and you say that I know that there are 100 centimeters in 1 meter. So the meter is the container and the 100 centimeters is the quantity that can be filled into that container. So you can see that this meter and this meter cancels out and you get 600 centimeters. So you can do it both ways, whatever works for you. All right, now low to high. Low to high is the simplest. Why? If you go back, you see all these factors, right? C is centi, 10 to the minus 2. K is kilo, 10 to the 3. And so if you look at low to high, if I say, tell me how many centimeters, how many meters are there in 1 centimeter, right? All you have to do is just replace this. We know that meter is the standard unit. What we want to do is we want to replace the factors, by their value. And what I mean by that is you look at C in the table, look at C right here, and you see what factor it has, 10 to the minus 2. So we replace that by 10 to the minus 2. And so that's how many meters that I have in 1 meter. All right, so I hope that makes sense. Okay, moving on. Measurement of length. So there are basically 4 tools that you can use. You have a measuring tape that can be used to measure distances between 1 meter to several meters. Okay. You've seen this probably in playgrounds, in athletic playgrounds, or when you're measuring your height, you use this. Vernier calipers. Vernier calipers measure between 1 centimeter to 10 centimeters. And the precision for this is 0.01 centimeters. The precision for the measuring tape is about 0.1 centimeters. The micrometer screw gauge is what measures the smallest of distances, less than 2 centimeters, and its precision is 0.001, my apologies, centimeters. And finally, the meter rod, it's used to measure distances up to 1 meters. And its precision is 0.1 centimeters, similar to the measuring tape. But one key difference is that measuring tape can measure longer distances and it can measure length of curved surfaces. So next up, a quick question. So at this point, you can pause the video, come up with the answer, and then keep watching the video, I guess, and see what the answer is. Now with this, what I'd say is, I'm actually going to ask you to attempt the question first before watching the video, because when you attempt it yourself, and even if you get the wrong answer, when you watch me do it, it's going to reinforce your concepts. So before watching, seeing the answers, I would say attempt it yourself first. Not at this point, maybe this one's too easy, but even in the future, this is something that I would suggest. So the circumference of a football, definitely we're not going to use a micrometer or a vernier caliper. It's going to be either a rule or a tape, but we know that, it's a curved surface. So the rule cancels out, and it's a tape. The measuring tape. Tape's answer option D. Okay, moving on. So what is measured using a micrometer? Area, current, length, mass. Now, as we move on into the course, we're going to see that we're going to learn about these concepts more, about these quantities more. So you will be able to answer this question more quickly. But for now, if we just use common knowledge, it's definitely not going to be area, because area is length times length. So it's going to be something squared, but we have a micrometer. So this is not the option. Current, it's a meter, so I don't think it's going to measure current, right? So current cancels out. Length, yes, maybe, but let's check the last option. Mass, nope. Mass, using meters to measure mass. Mass has a unit for of kilograms, so it can't be mass either. So the correct option's C. All right. Before we move on to the next question, there's just one thing that I want to point out, and that is that when we have these significant figures, let's say I have 4.123. This value, let's just say, before even I continue with this, let's say if I have the value 1 and I divide 1 by 10, that's equal to 0.1. If I divide it by 100, that equals 0.01. And if I divide it by 1,000, that is 0.001. So you can see, or you can tell, that this is the 100th or the 10th position. This is the 100th, and this is the 1000th. So this is the 10th position. This is the 100th position, because when we divide by 100, we get to this particular decimal point or this significant figure. And this is 1,000th. All right. Now I ask you to answer this question. But do not get confused, because it says 1/10 of a millimeter. And the answer choices are in centimeters. So what I'd suggest is, first convert all the values from centimeters to millimeters. How do you do that? You know that 1 centimeter equals to 10 millimeters. All right. So I can multiply all these values. And if you don't know how 1 centimeter equals to 10 millimeters, you didn't have to, but you did have to know milli and centi from here. Milli is 10 to the negative 3 and centi is 10 to the negative 2. All right. So if you know that, you can find this conversion. So yeah, okay. So 1/10 of a millimeter. So if 1 centimeter is 10 millimeters, then that means that if I multiply by 10, all these values, I'll get the conversion to millimeters, right? So 3.3 centimeters will be 33 millimeters. 3.31 centimeters will be 33.1 centimeters. This will be 33.10. Oh, sorry, this should be millimeters. And this is 33.12 millimeters. So the only measurement that measures up to 1/10 of a millimeter, not up to 1/10, but gives the value to 1/10 of a millimeter, is option B. Option C and D also give you up to a 10th, but they go to 100th. So we just want to see which goes to the 10th. So the correct option's B. Okay, so using a meter rule. All right, so the 3 steps that you should take for measuring a meter rule, or for making measurements with a meter rule, is first, the line of sight should be perpendicular. And what I mean by that is that you should be aligning your sight this way, that you're just perpendicularly, you're perpendicular to the, to the meter rule. Your line of sight is perpendicular to the meter rule. All right, and I'll explain why we should do that. That is basically to avoid the parallax error, but we'll come to that later. Point number 2 is take several readings and then take the average. For example, you remember when I said we were measuring the distance of that disc just with a meter rule. Let's not get into the tiny details. So for example, the first time I measured the length, I had 3. The second time I measured the length, I had 3.2. Okay, and again I measured the length and I got something else, let's say 3.4. So what I would do is I'll take the average of these readings to get a more accurate value. And that would be, how do you take averages? Averages, basically you sum up all the measurements and then you divide by the number of measurements that you did, which is 3. And you should get some answer, 3 point something. And that will be a much closer value to the truer value. All right, and then the third point is that do not take the reading from 0. And why is that? Let's say you're measuring with a meter rule, some object, but it might be that your meter rule is curved at the very edge, and that's where your 0 starts from. So you don't want to measure from 0, okay? What you do is you start from 1, okay? Because 1 is pretty much going to be a straight line, like a straight edge. But then whatever measurement you make, let's say I was measuring something and I measured some value at this point. And when I measured its length, starting from 1, that is, I got to this point. So that was the length. And it measured, let's say, 3 centimeters. But now it's not 3 centimeters because I did not start from 0. I started from 1. And so I have to subtract 1 from it. So I get 2 centimeters. All right, so parallax error is basically due to a thickness within the ruler. Due to this thickness, if there's a point here and your line of sight is here, what happens is when you look at the meter rule, your line of sight is going to give you a different value. It's going to give you 5 centimeters in this case. And if you look from the left, you're going to see 4.6. But if you look from the top, you're going to see the actual position. So, to avoid parallax error, we keep our line of sight perpendicular. Okay, using Vernier calipers, Vernier calipers, if you look at the syllabus now, you're going to see that it is not required, but I have, included this slide. But if you have any questions, just let me know in the comments, and I'll be happy to answer them. All right, the micrometer screw gauge. So with the micrometer screw gauge, you're going to have a main scale and then the thimble scale. Now you have to look for the divisions, what each division is in the main scale. In this case, it's not given, but I know what it is. It is basically 0.5 millimeters. So, this point right here is 5. This is 5.5. This is 6. And this is 6.5. So the reading on the main scale is 6.5 millimeters. All right. And what's the reading on the thimble scale? So if you look at the thimble scale, the values, they increase towards the top, right? So if this is 0, the next value is 1, 2, 3, 4, 5, and so on. So in the thimble scale, you see where the main scale coincides with the thimble scale. And that's going to be your measurement on the thimble scale. So it's going to be 46. Now, one thing to keep in mind is that all these measurements, each division stands for 0.01 millimeters. So when you read 46, you have to multiply that by 0.01, okay? So 46 times 0.01 gives you 0.46, right? And then you basically add that to this reading and you will get your final answer. So that's how you measure a micrometer screw gauge. Now the thing is, let's suppose you were not measuring anything. Like if you were not measuring anything at all, but you still see some value, that means that you have an error, right? I mean, I'm not measuring anything, so why am I seeing a value? So if that's the case, what happens is there are 2 cases. So there's the positive error and then there's a negative error. With the positive error, the thing is that so you weren't measuring anything, but there was still like the 0 of the thimble scale did not coincide with the thimble of the main scale, right? So the thimble scale is giving you a value of 0.06 millimeters, right? It's the 6th division where it coincides. So it's 0.06 millimeters. So if I'm not measuring anything, right, and I still get 0.06 millimeters, right? Whether it be 0.06 millimeters or centimeters, whatever this is calibrated in. I mean, if you know the calibration here, it says centimeter, but it doesn't matter. You just have to make sure that you're looking at the right units. So 0.06 centimeters, let's say, in this case, is the error that you get, right? And I didn't measure anything. So that means now whatever I measure, similar to the meter rule example, I have to subtract 0.06 from it, okay? The other case is that your 0 is to the top, right? And I told you that the values increase towards the top. So this is 1, 2, 3, 4, and so on. But below the below the 0, the values decrease. So this is, 49, this is 48, 47, 46, 45, and so on. So in this case, you see that the thimble scale gives you a value of 4, but it's negative 4. All right, and if I convert it to the scale, it's going to be 4 times 0.01, so it's negative 0.04. So I'm not measuring anything, but I'm still I did not intend to measure anything, but I still got 0.04 as my reading, negative 0.04. So that means whatever value you get, add 0.04 to it, okay? Because you're already measuring negative 0.04. So, I mean, you didn't measure anything, but you got negative 0.04. So whatever length you measure, you have to add 0.04 to it. All right, hope that makes sense. Okay, moving on. Scalars and vectors. So this is a very crucial, there's a very crucial difference between these two quantities. Now, all the quantities in physics, they're either scalars or vectors. Now, scalars are something that have a magnitude only. Like there's just a number that defines them. Let's say 6 or 7 or 2.1 or whatever. It can be anything, all right? Vectors, on the other hand, they have a magnitude and a direction. And we denote vectors by an arrow. So if this arrow is a vector, and I draw another vector, let's say this, they have the same direction, but vector B has a greater magnitude than vector A. So the length basically denotes the magnitude. All right, and if this vector is positive, then this vector is negative because it points to the opposite direction. All right, and the two methods to get the resultants. One's the tip to tail method, and the second one is parallelogram method. Now, the thing is, what's going to happen is that I'm going to draw two vectors at random. Now, I can move these vectors as long as I don't change their direction, okay? I can translate them anywhere I like, to the right, left, to 45 degrees. I mean, in the 360 degree range, I can move them everywhere, but I can't change their direction. All right, so what I'm going to do is, in the tip to tail method, you join the tip of one to the tail of the other. All right, you can't join tips with tips or tails with tails. You have to join a tip with a tail. So let's do that here. So let's take the first vector. So I simply translated it and I'm keeping the direction the same. And then I'm going to take the other vector. Again, I translate it, but I don't change its direction. So the resultant vector is going to be the tail of the vector. So from these two vectors, you look at the tail of a vector that's not connected to anything. So that's going to be your origin. And then you take a look at the tip of a vector that's not connected to anything, which is this one. And that's going to be your resultant vector. All right. The parallelogram method works in the same way. But in this case, you first connect tips with tips or tails with tails. So let's do that. So it's this way, the first one. And the second one is this way. Now, once I do that, I'm going to make a copy of both of them. So make a copy of this one, make a copy of the other one. And once I do that, now you look at the point where both tails meet, and then you look at the point where both tips meet, and you connect those points. All right, that's your resultant vector. They're both going to give you the same answer. Generally, I prefer the tip to tail method because it involves less steps. All right. So which quantities are both vectors? Again, you don't have to know all these quantities yet. We will study them in detail. So in this case, the quantities that are both vectors is answer D. Okay, two forces x and y act as shown. What is the resultant vector? So again, we look at the point that's just a tail and is not connected to anything. And we look at a point that's just a tip and it's not connected to anything. And we draw a vector between them. That's the resultant vector. And when you look at all these choices, this is the one that we get. So C is the answer. Right, again, list of various quantities is shown. How many of these quantities are vectors? Once you know all these quantities, you'll be able to better answer this question. But for now, the vector quantities are acceleration, displacement, force, and velocity. So 4. Acceleration. Vector properties. Now there's just 2 key things that I want you to know. First, if I have a vector like this, let's call this vector A. If I multiply this vector by some scalar magnitude, scalars only have magnitude, just a number that defines them. So if I multiply this, I shouldn't even be using the word scalars. Let's just say I just multiplied by some number. Let's say I multiplied by 2. So multiplying it by 2a just doubles the length of the original vector. All right. So that's important. If you multiply by 2a, if you multiply by 3a, this is going to get 3 times the length. Okay. The second thing that I want you to know is if this is vector a and I multiply it by -1, then minus a is going to be a vector that has the exact same magnitude, the exact same length, but it points to the opposite direction. All right, so these 2 things you should know, they're important. And now I will quiz you. So let's say I have this vector and I call this vector b. I want you to draw -2b. Okay, so here's how you draw -2b. So first I just take this part and I say, okay, 2b is just going to be double the length of b, and I account for the 2. Now I'm going to take care of the negative sign. So the negative sign just means I keep the magnitude the same, but I switch the directions. So this is -2b right there. All right. So state the difference between a scalar quantity and a vector quantity. Now a scalar quantity has magnitude only. I'm not going to write down the answers because that's going to take a lot of time. So let's keep it short. Has scalar quantities have magnitude, while vector quantities have magnitude and a direction. Then state 2 examples of each type of quantity. Just look at this table for now, and you can write down 2 scalar quantities and 2 vector quantities. So you got 3 points, just like that. Isn't it easy? Okay, moving on. So it says you have vector P and vector Q, and what it wants you to do is that it wants you to draw the resultant vector. But they said something very important here, and that is they said that I want you to draw the resultant vector to the same scale. Now, what do they mean by that? If they say to the same scale, that means that the scale is very important. What I mean by that is that you will take a meter rule when you're in the exam, and you will measure this vector length p. Let's say that vector length p was 3 centimeters. And then you will measure the vector length q, and let's say that was 1 centimeters. So now you draw vector q. You draw that over let me quickly erase this. So you have to make sure that you don't change the angles between them, in case if you change the angles, things can get a bit confusing. So what you do is you add a straight line like this. That's 1 centimeter long, and so that's q, remember? So I connected the tip of q to the tail of p. So what's my resultant vector going to be? Well, I look at the point where it's just the tail, and I go to the point where it's just the tip. So that's going to be my resultant vector r. Okay, but what is the magnitude of r? Like how much is r? For that, you will have to measure the length of r using a meter rule. So you measure it, and let's say when you measure it, you get, this was 3 centimeters. So you get something like 2.7 centimeters. So that's your resultant vector drawn to the same scale. Now, if they didn't ask you to draw to the same scale, you can just draw a rough drawing and that will work. But watch out for the same scale words. All right, more on resultants. Just a quick note that, if you have a right-angled triangle, if this is A and this is B, Pythagoras theorem states that the hypotenuse should be a squared plus b squared square root, right? And if I have this angle theta, right, I can basically get relationships between all these values. Let's say this is c equals to a squared plus b squared. So sine of theta says I'm equal to the opposite divided by the hypotenuse. Cosine of theta states that I am equal to the adjacent divided by the hypotenuse. And tan of theta states that I'm equal to opposite divided by adjacent. So that's what I wanted you to know. In the exam, if they give you a right-angled triangle, like if they give you two vectors that are at right angles to each other, like in this case, and they ask you for what the length of the resultant vector is going to be, you don't have to draw the resultant vector and then, come up with a, how should I put this? You don't have to draw a resultant vector. It shouldn't be, first of all, it shouldn't be oriented like this. My apologies. Like if they give you two vectors, like this and like this, you don't have to draw the resultant vector. You can just say that, the resultant vector is going to be, the magnitude is going to be a squared plus b squared square root. That's pretty much all you have to do. If they say same scale though, or if they ask you to draw, then you have to draw. But I just wanted to make sure that you know this, so it gets just if they ask you, and if you don't want to draw, you can just quickly calculate. Anyways, moving on. Okay, so just as an example, now again, they said a scale drawing, so we have to make sure that we are using a scale. And they also ask you to determine the magnitude of the resultant force and the angle between them. So let's say, in this case, you choose a scale. Now, you can choose a scale according to your choice. I'll say that 12 kilonewtons for me is 1 centimeter. You can choose any scale you like, right? So in that case, the 12 kilonewton force, I'm going to draw a 1 centimeter vector like this. And then, 36 kilonewton means that it's going to be 3 centimeters because I chose 12 kilonewtons to be 1 centimeter. And I'm going to draw 3 centimeters like this. And so what I do now is that I measure the length of the resultant vector with a meter rule. Now, if you want to measure it with a meter rule, you can, but you can also measure it using Pythagoras theorem, which is going to be basically, let's call this A. So A is going to be 3 squared plus 1 squared square root centimeters. So that's going to be the magnitude, but that magnitude is in centimeters. So you have to convert that into kilonewtons again, because that's what the forces were in. So you multiply whatever you get, that is A, by 12. And you put down that answer over here. And how do you calculate the angle? It says you want to calculate the angle between the resultant force and the north. So the angle between the resultant force and the north, what is that? It's this angle that it makes, right? And so if you want to calculate this angle, you have all the different lengths. You have this, and you also have A. So you can use any formula, tan theta, sine theta, cosine theta. Let's say in this example, I use tan theta. So tan theta is going to be opposite over adjacent, and you'd say theta equals to tan inverse 1 divided by 3. So that gives you the answer. Okay, moving on. Now, if you can do this, you have mastered resultant forces. All right. So attempt this question yourself first, and then come back. All right. So it says, the angle between the 3 Newton force and the 4 Newton force can be any value from 0 degrees to 90 degrees. Which value of r is not possible? Now, one thing to keep in mind is, that the angle between, let me just draw, this is 3 and this is 4. The angle, if the angle changes, the resultant vector is going to change, right? Let's say if the angle decreased, then the resultant vector is also going to decrease. Using the parallelogram method, it's going to become something like this. In this case, it was this. Let's say the angle increased. Now, if the angle increased, right, and I redraw this, then you can see that the resultant vector is changing the magnitudes. So how do we answer this question? Well, what we can do is we can just look at the extreme cases and see what the values at those extreme cases are. What we do know is that if I increase the angle, my resultant vector is going to reduce in magnitude. And if I increase the angle, my resultant vector is going to decrease in magnitude. And if I decrease the angle, my resultant vector is going to increase in magnitude. So let's look at that. Let's say I'm going to look at the value 0 first. So I have 4 newtons already. All right. So if the angle between 4 newtons and 3 newtons goes to 0, this vector of 3 newtons just overlaps this vector of 4 newtons. So if two vectors are overlapping each other, what I can do, and they have the same direction, I can just simply add them up, right? 3 newtons plus 4 newtons equals to 7 newtons. But the thing that's important is I can only do this like this if I have the same direction. So it's 7 newtons. So I see that, 7 is a choice. So I'm, that's a possible, that's an option. Like that's something that I can have. All right. Now let's look at the other extreme case, which is 90 degrees. So for that, let me draw the 3 and the 4. Now in this case, if I draw the resultant vector, say like this, using the parallelogram method, oops, there are some dogs barking. I hope you can't hear them. Well, if you do, I'm so sorry. Okay, 3, and then this is, 4. Just redrawing those vectors. And now if I calculate the magnitude, well, what do I know? I know that this is 90 degrees, so it's a right angle triangle. So if I want to calculate the resultant vector, I can do that by c equals to 4 squared plus 3 squared square root, which is going to give me 5. So I can see that as the angle increased, the resultant vector, the magnitude of the resultant vector decreased. And it can decrease as much as, it can decrease to as much as 5 newtons. All right. And it can increase to as much as 7 newtons. So my range is 5 newtons to 7 newtons. So all these options are correct except 4. So this is not possible. All right. So now that we've covered the first chapter, physical quantities, units, and measurement, let's just briefly overview the learning outcomes and see if we've learned all of them. So define the terms scalars and vectors, check. Determine the resultant of two vectors by a graphical method, check. List the vectors and scalars from distance, displacement, length, speed, velocity, time, acceleration, mass, and force, check. I'm checking it. When we move on to the further chapters, you're going to be able to tell the difference much more easily. Describe how to measure a variety of lengths with appropriate accuracy using tapes, rules, micrometers, and calipers. The use of Vernier scale is not required. Check. Describe how to measure a variety of time intervals using clocks and stopwatches. All right, so this is something that we've not covered. And that is going to bring me to an important point that I'm going to mention in the next slide. But before I do that, let me just quickly tell you something about tape timer, a ticker tape timer. Basically, let's say I have this tape. And at this point, I have a pencil that's moving up and down at a constant frequency. It just keeps moving up and down, all right? And I'm not touching it. It just comes down and then goes back up. And what I do is I have a thread here attached and I'm holding it. And I'm slowly pulling the piece, the strip of paper towards myself, to the right. So when this piece of paper is going to start moving to the right, let's say at this point, and let's say the pen came down, it left a mark. And as I'm moving, this moves further to the right, and the pen keeps on marking the ticker tape, the sheet, the sheet that I have. So this means that let's say if I have something like this at the end of the day, what does this tell me? This tells me that when I was pulling it, I was pulling it at the same speed, or like I wasn't like slowing down or increasing or speeding up. I was just pulling with a constant speed, whatever that speed was. But if I have something like this, let's say, all right, this means that initially I was pulling it very slowly, and so when I was pulling it very slowly, it left 2 dots. But then I pulled it much more quickly, and so it gave the pen less time to leave a dot, and so the speed has decreased. But that's all I wanted to say about the. I wanted to talk about the ticker tape timer, but as far as this point is concerned, I wanted to mention that in the very next slide, which I will. And recognize and use conventions and symbols contained in science, symbols, and systematics, Association for Science Education. I mean, this includes the subunits and everything, but you can look at it. This again brings me to the next point in the next slide, which is quick reading. Whenever you watch these lectures, I'm pretty sure that the concepts are going to be clarified. But see, the thing is, even every book that you have, right, all of those books serve as reference books. All right. So there is no book that covers 100% of the syllabus. So what I want you to do is, after you go through these lectures, I want you to give a very quick reading of the book chapter. I mean, as you read, you're going to know pretty much everything. But if there's something, let's say, something very minute that we did not cover, the reading is going to give you that information. And so that's why reading is very important. And the second thing is practice past papers. And what you can do is, there are 2 ways. You can use a topical. They're good because, all the questions are already in a specific topic. But if you don't have access to a topical, I have included the links to these past papers. You can find the past papers from, I think, 2001 onwards for O-Levels and physics. So this is for O-Levels, and this is for IGCSE. And another thing that I want to mention is Z Libraries. Basically, this is a website where you can go to and download any book that you'd like. Mostly the books that I need for my education, or in college or whatever, I can usually find them on Z Libraries. And I've downloaded David Sang's physics course book, which I've heard that is a good course book for O-Levels, for teaching O-Levels and IGCSE physics. So I've included the link to that as well. Or you can just go to Z Libraries and search for it. And the last thing that I want to mention is, but before I do that, I can't emphasize enough on practicing past papers. It's actually going to be much easier if we study one topic, and after we study one topic, you go to the topical book, or you go to the past papers, and you at least and you start solving questions just from this topic. Because what happens is, because now we're just covering physical quantities, units, and measurement, you're only going to solve maybe like 1 or 2 questions from each year, right? So by the time we finish this course, you're going to have solved many past papers, and it's going to take less time, right? Because solving the whole past paper in one go is going to take more time, but solving it topical wise, as soon as we finish a topic, you just attempt the questions related to that topic. That is going to be much quicker, and it's going to be much more efficient. So yeah, do that. Practice a lot of past papers, and that's definitely going to help. And the last thing that I want to say is that I have this email that I've specifically made for my tuition lessons. So if you have any question, right, just email me at this email, and I'll try to get back to you before the end of the week. With that, thank you so much for attending my first lecture. If you liked this video, then please subscribe to the channel and give a thumbs up, and I will see you in the next lecture.